The signed area. Let's consider the signed area. If I have a curve f of x here, and it crosses the x-axis at c, and I want to take the integral from a to b, well, a1 here, let's say I give it a numeric value of 12 square units, and a2 in green below the x-axis, let's say I give it a numeric value of 4 square units. Well, if I'm taking the integral from a to b, I'll get the algebraic sum of a1 and a2. So if I integrate this and I'm looking for the area under the curve, I'm going to get 12 plus a negative 4, which is 8 square units. When you integrate from a to b this way, it's called the signed area, and it's associated, if we're talking about kinematics, it's associated with displacement. 12 plus a negative 4. That's going to give me something called the signed area. If, however, I have the same drawing and the same curve, f of x, and I want to find the shaded area, in other words, all of the area here plus all of the area there, I have to take the integral of a to c of f of x dx, that's a1, which is 12 units, and add it to the opposite of whatever I get here below the x-axis. The opposite of that would be minus 4. So I will get 16 square units for the total shaded area. This is associated, if we're talking about kinematics, this is associated with distance, total distance. So if we're given a function and we're asked to evaluate it from a to b of f of x dx, in other words, find the area under the curve, we have to realize that this expression, the integral of a to b of f of x dx, only gives the correct area if f of x lies above the x-axis over the interval in question from a to b. If f of x crosses the x-axis, we must evaluate each region separately. If we don't do that, so otherwise we'll be reporting the signed region. So here are the important steps for finding areas. First, you want to sketch f of x over the interval x equals a to x equals b to determine if there are any x-intercepts. Alternatively, we know to find the x-intercepts, we set y equals to 0. So we could have our function, say it's x squared plus 2x plus 1 was equal to y. Well, we can set this equal to 0, and that expression there will give us our x-intercepts. If we do have x-intercepts over our particular region from a to b, we want to integrate y equals f of x separately over each region. That's only if necessary. So if we do have something up and then below the curve, we want to integrate the one above the curve and then the one below the curve. If we do have anything below the curve, we're going to put a minus sign out in front to make all terms positive, and then just add up those positive terms. Let's do an example to see how this works. Here's an example of finding the area bound by a curve in the x-axis, considering that the curve in our interval from 0 to 2 crosses the x-axis. Find the area enclosed by the curve y equals x cubed minus 1, the x-axis, and from 0 to 2. In other words, from x equals 0 to x equals 2. Well, my first step is, does this cross the x-axis? So I can set x cubed minus 1 equal to 0. So x cubed equals 1. If I take the cube root of both sides, x equals 1. I know I do have an x-intercept there. If I graph this on the graphing calculator, or I simply chose more points, I get something that looks like this. So I know I've got this region here, which is negative, and this region here, which is positive. That's going to help me to integrate. The expression I'm going to use to integrate is, I want to integrate from 0, my lower bound, to 1, and I'm going to take the opposite of that because I know that's a negative number. I'm going to take the opposite of a negative, which will give me a positive, of x cubed minus 1, I put that in parentheses, dx, plus, I'm integrate from 1 to 2, and I know that's above the x-axis, so that's positive. 1 to 2 of x cubed minus 1 dx. So I'll get the opposite of, this will be x to the 4th divided by 4 minus x when I integrate this. You have to know your integration rules to follow me, from 0 to 1, plus, and I'm just going to have this from same expression, x to the 4th divided by 4 minus x from 1 to 2. Well, this whole expression simplifies to 3/4, and this whole expression here simplifies to 2 3/4. So ultimately I wind up with 3.5 units squared. What is that? That's this, the opposite of this, plus this. That gives me the total area under the curves, or trap between my curve and the x-axis. This is not the signed area because I took the negative, the opposite of this.